Hi everyone, my name is Adam Denchfield. I'm a graduate student at UIC, and based on the exciting work being done at CDAC on the Hydrides, I'd like to tell you about the quantum zero-point motion of hydrogen-based compounds. So first, what is zero-point motion? Well, it refers to how the nuclei in a system are truly extended dynamical quantum objects, even at zero temperature, as compared to the classical case. An important question to ask is, how does this affect the stability and superconducting temperatures of hydrogen compounds? Well, in lanthanum hydride, including quantum effects actually stabilizes the cubic phase at high pressures, and in H3S, including these effects leads to a more accurate pressure versus critical temperature phase diagram. There are a lot of methods that have been used over the years to study this, but before there were computers, there was pen and paper and toy models, and the results seem to suggest that phase transitions are suppressed by quantum zero-point fluctuations. However, in lanthanum hydride, as I just showed you, we actually see the opposite, meaning that the advent of computers has taught us a lot of new things about zero-point motion. Density functional theory is a clever construction whereby one replaces many electrons in your system with an electron density interacting with the static ions. It's variational in the electron density and can get you the ground state energy and electron density of your system. Another method that was initially proposed in the 1950s was the self-consistent harmonic approximation. It's only recently that we've been able to actually use it, because now is when we have powerful computers. It's a variational method, much like density functional theory, but the parameters you vary are actually the vibrational properties of your system. And while I won't go into the details, this method can capture thermal and quantum effects in your system. Density functional theory has been used to analyze the possible effects of zero-point motion in H3S. You can take an H3S crystal structure, randomly displace the atoms, and ask what the effect is on the density of states, for example. Zooming in near zero here, we see that the disordered phase actually has a peak that's higher and closer, well, a peak that is closer to the Fermi level. That typically means that the superconducting temperature of this system is increased. So it's important to ask whether or not we can actually figure out if this is the case. Well, density functional theory alone can't tell us that. SSCHA is an improved method. On the left and the right, I show platinum hydride and lanthanum hydride. Outlined in purple, I show how the hydrogen frequencies gained by density functional perturbation theory are actually increased when you include these quantum and thermal effects. This happens for both systems. Now, when the vibrational frequencies are increased, one would suspect that the critical temperature would increase. However, the electron-phonon coupling is reduced when you include these effects, and unfortunately, the net effect is to reduce the critical temperature in these systems. In green for both systems, I outline where the SSCHA method correctly predicts stable crystal structures by having non-zero energies, whereas the DFPT methods incorrectly predict structures breaking down. In summary, going beyond static DFT is going to be necessary for the hydrides. The SSCHA method can capture some of these effects, and one way to extend it is to incorporate post-DFT methods into it, like DMFT. Thank you.